Good day and welcome back for part 3 of our discussion on differentiating the inverse trig functions. In our previous videos, we've reminded ourselves how we define the inverse cosine, the inverse sine function, and developed associated differentiation formulas. What I would like to do in this video is the same thing, but just for the inverse tangent. And a first step towards defining the inverse tangent function requires us to have a graph of the tangent function itself. So I would like you to pause the video and draw a graph of the inverse tangent function. And the reminder I have for you with the inverse tangent function is, remember, it's kind of just repeating the same pattern over and over again. When we think of y equals tangent, tangent is sine over cosine. So whenever cosine is equal to 0, this tangent curve is going to have an associated vertical asymptote. So at plus or minus pi over 2, plus or minus 3 pi over 2, and so on. And if we look at just kind of, one period of the tangent function between x equals minus pi over 2 and x equals pi over 2, graphically we get the following curve. It passes through the origin. As you go towards pi over 2 from the left, tangent is going to infinity. As you approach minus pi over 2 from the right, tangent is approaching minus infinity. Now, this is just one period. Note, it just keeps doing this over and over again as you move to the left and the right. But if we restrict ourselves to this single period of the tangent function, note the graph is 1 to 1, it passes a horizontal line test, and it hits every possible output. The exact characteristics we are looking for to define an inverse function. So note, arctangent of x is defined to be equal to y precisely when tangent of y is equal to x. And similar to our previous definitions of the inverse trig functions, we need to suitably restrict these inputs to force the function to be 1 to 1. So we also have this restriction that the input y going into the tangent function must be strictly bigger than minus pi over 2 and strictly less than pi over 2, because the tangent is not defined at either of those values. And once again, notationally, if you prefer, you could certainly write this as tangent to the minus 1. But once again, just be careful with that notation. It can occasionally lead to some rather silly mistakes. And in terms of some characteristics of the arctangent function, by inspection, we can see that the arctangent, its domain, are going to be the outputs of tangent, so minus infinity to infinity, and its range will correspond to the restricted domain or inputs for tangent, minus pi over 2 to pi over 2. And in the case of the inverse tangent, there are a couple limits that have a tendency to appear. So because of that, I'm going to sketch a graph of the inverse tangent function. What I would like to recall for you is that graphically, if we have a function and we would like to sketch its inverse, we need to take a reflection about the line y equals x. And it's sometimes kind of hard to see the reflection, but remember what a reflection actually does across the line y equals x. You just switch every x and y. So intuitively, the vertical asymptotes are going to become horizontal asymptotes. So in the inverse tangent function, it will have two horizontal asymptotes. Y equals minus pi over 2 and y equals positive pi over 2. And graphically, inverse tangent is the curve I've sketched in blue. And what I would like you to do is to hopefully tell me without too much hesitation what is the limit as x approaches infinity of arctangent? What is the limit as x approaches minus infinity of the arctangent? So pause your video and fill in those values. And note, for a large positive input, the arctangent curve is approaching that horizontal asymptote, y equals pi over 2. For a very large and negative input, the graph of arctangent is approaching that other horizontal asymptote, y equals minus pi over 2. So we have two associated limits that will potentially be of interest in future sections. When it comes to differentiating the arctangent, we can use the same exact approach that we used with the natural log, the inverse sine, and the inverse cosine. And since we've done it 3 times, I'm not going to go through the details, but instead I'm going to write down that associated formula and invite you to think about the details. The differentiation formula for arctangent of x is 1 over 1 plus x squared. And a very nice corresponding indefinite integral would be that the antiderivative of 1 over 1 plus x squared is equal to the arctangent plus c. Certainly formulas that we need to know and be familiar with. At this point, we've really finished discussing kind of the key properties we wanted to hit on. How the inverse trig functions are defined, associated differentiation, anti-differentiation formulas. But there's a lot of information here that we need to be familiar with, so let me attempt to summarize this all. So to summarize, let me recap the information we've had combined from the previous 3 videos. We define y equals arcsine of x to mean that sine of y is equal to x, with the restriction that that output for the inverse sine, the y value, would be how we had to restrict the domain of sine to force it to be 1 to 1. So between minus pi over 2 and pi over 2. For arc cosine, we say y equals arc cosine of x is true whenever cosine of y equals x, and we have this restriction that the y value is between 0 and pi. And as we defined a moment ago, for arctangent, we would need tangent of y equals x, and that y value to lie between those 2 vertical asymptotes that restrict it, tangent, to force it to be 1 to 1. The associated differentiation formulas. The derivative of arcsine, 1 over the square root of 1 minus x squared. The derivative of arc cosine, the opposite of that. And the derivative of arctangent, 1 over 1 plus x squared. Furthermore, note there are 2 associated anti-differentiation formulas we should be familiar with. The antiderivative of 1 over the square root of 1 minus x squared is arcsine plus c. And an antiderivative of 1 over 1 plus x squared would be arctangent. So once again, this completes our discussion of the key properties and formulas, but as usual, what remains is going through and practicing examples. In the upcoming videos, we will work through several more standard types of examples, and there will even be a class-type worksheet for you all. But this is an opportune time to go back to those suggested problems in the book and begin practicing there as well. So when you have questions, do not hesitate to contact me. Stay tuned. Take care.